So watch, I'm going to sweep counterclockwise from the 3 o'clock position. So that the angles cut off 1 radius length of arc length. And so that corresponding angle of openness is, angle measure is 1 radian, right? 1 radian. So then if I keep doing that, every time I mark off a radius length, I've added 1 more radian of openness to my angle. So here's 3 radius lengths of arc length, making an angle of 3 radians. And so when I go all the way around, so then we get all these spots on the circle for whole numbers of radius lengths corresponding to whole numbers of openness in radians. And so then exactly halfway around the circle is how many radius lengths? Pi. Exactly halfway around the circle takes pi radius lengths. 3 and some change. 3 and about 15% of, or 14% of a radius length. And then to get it exactly right, we need all the decimal places to infinity. 3.14159. Some guy recited like millions of them without stopping. It took him 5 hours. Okay. So that's what we're doing. So now, remember we started with the 3 circles. What was the radius of this circle? Do you remember? I've zoomed way in now. You see what that is? Yeah, so this first circle, when we had the 3 circles, had a radius of 1. So this is the point. What ordered pair is that right there on that circle? 1, 0. And the top of the circle? X is 0, Y is 1. And the center is 0, 0. So when you have a circle with center 0, 0 and radius 1, that's called the unit circle. Okay, the unit circle. So is the unit circle a specific circle? Is it a specific circle? It has a given radius and a given center. So is it a specific circle? Is it one circle? Seems like it, but we're actually going to conceive of this or think about this as every possible circle in the universe. So we have an ant walking in a circle with a radius of 14 millimeters. Okay? And then we have a moon going around a planet, and its radius is 8.8 billion miles. Both are going in a circle. 2 very different circles, right? The ant is crawling in front of you, in front of your notebook on your desk. It's crawling in a circle, 14 millimeters radius. The moon has a huge radius relative to that. Okay? So how can this circle be thought of, or how can both of those circles be thought of as the unit circle? So what we would ask is, this point here, 1, 0, bigger. How can we think of, say, the circle for the ant? What would this point mean then, this ordered pair 1, 0, if this is the circle of the ant walking in a circle of radius 14? What would the 1 mean? 1 would stand for what? 1, yeah, 1 what? 1 meter? Which is? Right. So it'd be like 1 radius of 14 millimeters, right? So this would be like 1 radius length. And if it's 1 radius length and it's the ant, then what is the radius length in millimeters? 14. So that 1 is measuring how many radius lengths, right? So we're 1 radius length to the right. And so if we're talking about the ant, then we know we're 14 millimeters to the right. And if we're talking about the moon, then what does that 1 mean? flying around his planet. Does it mean 14 millimeters? No, it means that you've got one radius of 8.8 times 10 to the ninth miles. Does it make sense? So in this way, when we think about these coordinates on the circle, of the unit circle as number of radius lengths, then it can represent any circle, every circle in the universe that we could possibly think about. So it is, so yes, it's kind of one specific circle, but we want to think of it as applying to any circle, and then to do that, this one up here stands for how many radius lengths. Okay, so here's our ant. Our ant's walking around like this, and our ant gets right here. And if I look here, I really wanted that to be a better place here. Let's try that again. So the ant is here. This is what I meant. So how far above the x-axis is the ant? How far above the x-axis is the ant? 0.5 what? Radius length. Do you see that? So if the ant, when the ant stops right there, if the ant is 0.5 radius lengths above the horizontal axis, then how many millimeters is he above the x-axis? 7. Do you see that? So knowing that this is measured in radius lengths, then we could find for the ant. So we could say, oh look, the ant now is currently 7 millimeters above the horizontal axis. You see that? And then what about the moon? So it's the same thing. The moon's going around its orbit, and it stops there. How many miles is the moon above the horizontal axis? 4.4 billion miles, right? 4.4 billion miles. In both cases, the object we're looking at is 0.5 radius lengths above the horizontal axis. Okay, so this is going to set this idea right here sets the stage for what we're going to do the next couple weeks. Okay, super powerful idea. That the unit circle, locating these coordinates on the circle in terms of radius lengths or fraction of a radius, right? Because the 1 is going to be the biggest it ever gets, right? You'll never be more than 1 away. So then all those distances will be a fraction of the radius length. And so then if you knew the radius of your particular circle in context, and you have the fraction of the radius length, then it's easy to get, how many miles or how many inches or how many feet that corresponds to. Okay, does that principle make sense? The unit circle can represent every circle by considering these values on the axis as number of radius lengths or fraction of a radius length. Okay, open up to page 269. Okay, so it should be talking about a bug on a fan, is that right? Okay, so these questions should be review. These questions should be review type questions in terms of distances traveled, angles marked off for this bug. It's going to start at the 3 o'clock position. It's going to start at the 3 o'clock position, and the fan's going to rotate counterclockwise, like we've been saying. And then they're asking you some questions about arc lengths and angles and things like that. Oh, so what's the radius of the fan? Let's write that down. The radius is 2.6 feet. So go work through those questions. Work together. You're either making progress or you're getting help. Those are your 2 options. You're making progress or you're getting help. got you. I know you.
Yay, no.
One of the lucky ones. Okay, so if the bug travels 5.2 feet, how many radians does it travel? No calculator necessary, right? You just recognize what is 5.2 relative to our given information. It's 2 radius lengths, right? It's 2.6 times 2, which is right there. Okay, so arc. Oh, where's the arc? I guess I just got rid of that. Okay, so that's two radius lengths right there. Why? Because it's 2.6 times 2. So that's an angle measure then of 2 radians. Openness of 2 radians that the angle that the. Okay, what about 11.7? So now it's going to go 11.7. What is it? Feet? 11.7 feet. And so if we want the angle measure in radian, we're really calculating what? If it's 11.7 feet. So S is 11.7. We want the radian angle measure. We really want to know what? How many radius lengths the bug went? How many radius lengths of arc length the bug went? That'll be the same as the rotation in radians. So how do we get how many radius lengths it is if the total arc length was 11.7 and the radius is 2.6? Yeah, you're going to say how many times does 2.6 go into 11.7? So practice this reasoning rather than what's the formula, and I'll just use the formula, okay? Because you're going to be responsible for the reasoning, okay? So yeah, we got a total arc length of 11.7. By dividing, we're saying how many 2.6s make up 11.7, or how many radius lengths? And what do you guys get for that? What? 4.5. So 4.5 radius lengths of arc length means 4.5 radians of openness. .5 radius lengths of arc length means 4.5 radians of openness. Okay, so let's go down to number 7. So 0.6, if the bug goes 0.765 radians, that's the same as 0.765 what? That's the way we want to think about this. Oh, so if it's an openness of 0.765 radians means an angle or an arc length of 0.765 radius lengths. So how many feet did he go? So if the bug went 0.765 of a radius length and a radius length is 2.6 feet, how far did he go? 0.675 of that fraction of 2.6. And you got what? 1.99 feet. Almost 2 feet. Pi over 2 radians. Pi over 2 radians is not, pi over 2 doesn't mean just a place on the circle. It means a number of radius lengths or an openness in radians, and it takes you to the very top of the circle, right? So we want that is some number of radius lengths, pi over 2. And we're going to take that many times 2.6. And we get? Nice and loud. 1.35 feet. Oh, 1.3 pi. What is 1.3 pi? 0.0. So for the bug to travel to the top of the circle would be 4.08 feet. Why? Because it's pi over 2 radius lengths, or pi over 2 amounts of 2.6 feet. 4.08 feet. Questions on these problems? Review. So now, more than just arc length and angle measure and radius, that's what these are about. Now we want to actually talk about the location of the bug as it travels. The location of the bug as it travels. We want to think of this as a dynamic situation, right? Quantities are changing together. So our input quantity is going to be our angle, right? The measure of the angle swept counterclockwise from the 3 o'clock position. Burn this in your brain. You're going to have a quiz on it, and it's the land we live in. The input quantity is going to be the measure of the angle swept counterclockwise from 3 o'clock, usually in radians, but it could be any angle measure, okay? It could be any unit of angle measure. Oh, maybe it's that. Oh, that's what I wanted. That's what I wanted before. Okay, so that's going to be our input. And then our output we want is to be to reference the location of the bug for that angle swept. So as the bug sweeps out an angle, it's sweeping through locations, right? Locations. So if we want the location of the bug, we actually need two quantities to keep track of that location. And so the first quantity is going to be relative to what we call the horizontal diameter of the circle. And so if we're after the location of the bug, what quantity relative to the horizontal diameter are we looking at? And I've given you an illustration of it there. So what quantity relative to the horizontal diameter will help us determine the location of the bug? Yeah, so height, or so like vertical distance, right? Vertical distance output. So for function number 1, the output's going to be the vertical distance above the horizontal diameter measured how? So we talked about this earlier. To be universal and generic, we can measure that in a fraction of a radius length. We're going to measure the vertical distance above the horizontal diameter in the fraction of a radius length. So let's just practice that here. So what would the value of that quantity be right now? The vertical distance above the horizontal diameter as a fraction of the radius length. What would you estimate it to be? $10, 5, 0.5, 0.1, -6? What fraction of a radius length is the bug above the horizontal diameter? Anyone want to guess? I heard 0.8, 0.9. What do you think of that? Yeah, that's the idea, right? So this is a whole radius length right here. So the bug is almost one whole radius length. To me, it looks like about 4/5 of the way up, right? About 4/5, so like 0.8. So the value of this quantity for this angle, so we've got an angle, input, and then we have the output. The current output would be about 0.8 vertical distance above the horizontal diameter as a fraction of the radius length. We'll try one more example. This is huge for the next 2 or 3 weeks, so don't tune out. Okay, what about now? So for this particular angle, what's the value of this output quantity? Vertical distance above the horizontal diameter as a fraction of the radius. Yeah, so first of all, since we're measuring above the horizontal diameter, how are we going to mathematically show that we're below? Negative, right? Negative. So then negative what? What fraction negative are we of the radius length below? 0.4 or 0.5, something like that. So negative 0.4 or negative 0.5, something like that. I'll just say negative 0.4, okay? So that's the idea. So then that gets us the vertical position of the bug for any angle, right? That's function idea, right? Input angle, for every given angle, we can track the vertical distance. But is that all there is to the location of the bug? What else? Yeah, so we can talk about the vertical diameter, and we can look at what? The bug's horizontal distance to the right of the vertical diameter, also measured in fraction of a radius length. So that's what I'm showing here. So there's our vertical diameter, and I'm showing with that red horizontal line the bug's horizontal distance to the right of the vertical diameter. Okay, estimate it right now. So what the second function, the output of the second function, the horizontal distance to the right of the vertical diameter as a fraction of the radius length. Estimate it. What'd you say? He wants negative 0.2. People are nodding. What do you think? Yeah, so first of all, negative. Why negative? Because it's to the left. So if it's to the left of the vertical diameter, it'll be negative. If it's to the right, it'll be positive. Okay? And so we're to the left here. So how far to the left are we of one radius? You said negative 0.2. So you said negative 0.2, negative 0.3, right? Yeah, right around there. So negative, we'll say negative 0.2. That's good. And let's go back to our function 1. So we're at the same spot. What is the vertical distance above the horizontal diameter as a fraction of the radius length? Vertical distance above the horizontal diameter as a fraction of the radius length. What would you say for this one? Someone over there? What would you guess? Let's see. Marshall, what would you say? 0.9. Or 0.9, even 0.95, right? It's almost very close to the top. You can say 0.9, 0.95 is the fraction of the radius length up, and negative 0.2 is the fraction of the radius length to the right. So it's left because it's negative. Okay, let's do another one. So let's get them both going here, both at the same time. So then I've got a little thing helping you see the output of the first function, right? Over there. So let's do this. Let's just tap it right. Okay, go. So let's without your calculator. So how about estimate the angle, estimate the input in radians. Estimate the input in radians. So estimate three things. The input in radians, just your eyeballing based on your understanding of it. And then estimate the output of function number 1 and the output of function number 2. And compare with the person next to you. Those three things. Estimate those three things. Okay, compare. So either making progress or you're talking. So talk or comparing. Compare what you're saying. So Okay, Ali, you're up. What's your estimate for the value of the input here, a radian measure of the angle? Not sure. Lewis, right? Taylor? Okay, sorry, Taylor. He said about 4 radians. Good, because we know 3 is here, right? 3 is right there, so that looks up pretty close to 1 more radius length, so something around 4. And then what'd you say for the input of function 1, the vertical distance above the horizontal diameter? Keep going. Negative 0.7. It's below, and yeah, that's pretty good. That's like 70% of the way down. Negative 0.7. Okay, someone new. Tofi, did you get the value of function number 2? Negative 0.6, she said. So negative because it's left, and then a little bit further than halfway. Negative 0.6. Good. Is this making sense? Okay, so this you're going to see this is the basis of trig. So many of you have had trig before, and you haven't ever thought of it this way, but this is the foundations of trig. Locating a position on the circle with coordinates that are fraction of the radius length. So this horizontal distance to the right is really the same as what familiar thing? So this distance right here is really the same as what familiar thing you've been dealing with your whole math career. X coordinate, right? So what are we estimating that to be? Negative 0.6. That's the output of function 2. Right? The output of function 2 is like an x coordinate. And then the y coordinate is like the output of function 1, vertical distance. I could also show that right here on this bar. Right? So the outputs of these two functions then are the coordinates of the bug, and that gives us the location of the bug for the given angle. Okay, let's do one more example. Let's do it right here. A little bit. Okay, again, estimate all 3. Nicholas, right? Tell me. So what did you think of the angle measure? What did you estimate for the angle measure?
I said 3 radians.
Okay, 3. So maybe a little less. Maybe a little less than 3. And actually, if you look down here, to be exact, it's 2.8. So he said 3. That's a good estimate. It's actually 2.8. All right. Value of function number 1. What'd you say? 0.4. 0.4. What do you think? Yeah, it's positive because it's above the horizontal diameter, and it's not quite halfway. And then number 2.
Negative 0.9.
Negative 0.9. It's almost all the way to the left as a fraction of the radius. Questions? Okay, so for Monday, you got quiz prep, you'll have web work, and then we usually do homework on Mondays, right? Yeah, and written homework. Check Blackboard. Have a good weekend.